David Smith here with one more flipped classroom math video. 3 tips before we start. First, remember you can speed up the playback if that helps you get through the video faster. Just make sure you understand and keep up with your notes. Second, you can pause the video at any time to catch up with your notes or think about the topics. Lastly, you can turn on the captions and watch my words go by on the bottom of your screen. This video goes out to my 2025-26 Algebra 2 and Modeling class. We've been working through the Fireworks chapter as a piece of a larger unit on quadratics, and we're getting ready to have our test. And so today in class we solved the unit problem. And I had a couple students say, hey, could you record a video on that so we could watch that and master the thing a little bit better? And yeah, that's what this is. Now, I want to say something. If you're working through the Fireworks unit and you have not been prompted to come up with the solution to that unit problem, you may wish to not watch this video yet. Your teacher is probably planning a gradual reveal in terms of the techniques and what you need to do to solve that unit problem. So you don't want to steal their thunder. However, if you want to watch it, that's okay with me. So here we go. There's a firework rocket. You know, you have a firework display, 4th of July, and they shoot fireworks up and they explode. Those fireworks are carried on a rocket, and that rocket is shot from a 160-foot high tower because they want to get a lot of height, so they started at 160. And it's the height of the rocket is given by this equation or this function. Height as a function of time. So what that means is as time goes by, the height is going to change. The rocket's going to go up first, and then it's going to hit the height, and then it's going to come back down to Earth. Because we know gravity is going to pull that thing all the way back down to the ground. So here's our function. 160 plus 92t minus 16t squared. Now let's break that apart a little bit. When time is 0, right before it's launched, these two terms are 0. And so that tells you that it starts at 160 feet high. Sweet, we actually already know that. We were told that here. This is the y-intercept, by the way. If you know your quadratics, this one's written in the opposite order. We're going to change that in a little bit. But the number term, no variables, just the number term, that is always the y-intercept. This number is the initial velocity, and it's just a number that goes in this equation to reflect the rocket's initial velocity. If it went faster, this would be a bigger number. If it went slower, this would be a smaller number. This is just determined experimentally. Finally, this term is the force of gravity. And the force of gravity is pulling down on the rocket the whole time. Even though the rocket's going up at first, then it's going to lose its power, and then gravity's going to take over and pull it down. So that's why this is a minus. And then the squared is that because gravity is an exponential force, and it's going to pull it down faster and faster and faster. So that's why we have a squared there. Any function on Earth that's tracking like a thrown object or a launched object is going to have a minus 16t squared. Okay, so your first prompt, and this should always be something that you think about. When you have a situation like this that's out there in reality, draw a picture. It's going to help organize your thoughts and make sure that all your calculations are correct. So pause the video and draw a diagram representing this situation. And there's like maybe 1 or 2 numbers that are in here that you can put on that diagram. Okay, let's see how you did. I sketched this on a coordinate plane because we do need to be on the coordinate plane. We're needing to figure out times and heights and all that, so we need to throw it on the graph. So my horizontal axis, usually x, that's the independent variable. In this case, it's going to be t, which is time. Height is dependent on time. The time is different, the height is different. So t, my x-axis, I'm going to call it a t-axis, and my units here are seconds. And then my vertical axis, h of t, height as a function of time, you can call that y if you want, but we use function notations in situations like this. H of t is the height, and that's the vertical component of the rocket's trip. And then, of course, the units for that one are feet. And then finally, my number, that's 160. It's launched from 160 above the ground. So there is my diagram. Okay, here we go. Questions. This is what the unit problem is asking us to find. So here's our first question. When does the rocket achieve its maximum height? Perhaps they want to time the explosion of the actual fireworks so they happen right when the rocket hits the top. So they need to set the timer on that, or the short fuse, or whatever that is. They need to set that so it goes off when the rocket is at the highest point. So they need to know that time. Second thing, what is the maximum height? Perhaps they need to know that so that the embers that come down don't hit people. It has to be high enough so that they all fizzle out before they ever get down to the ground. So we need to figure out the time it takes to get there, and then what the there is. Now, pause the video, and I want you to look at your graph, at your diagram, and mark that spot that we're all curious about. These two questions occur at one place on this graph. Okay, if you said the vertex, you're right. And if you marked it right there, that's the vertex. That's the turning point of this parabola where it goes from increasing to decreasing. Or in terms of the rocket, it's where the rocket goes from climbing up to then falling back down to Earth. That's the vertex. This parabola opens downward, makes sense in the situation, and it also makes sense for the equation, because remember we had the minus 16t squared. That minus 16 is our a term on our quadratic equation. So, we identified that it's the vertex that we're interested in. So, pause the video and make some notation on your graph about what that time would be and what that height would be. You don't know the numbers yet, but you can mark their positions on the graph. The coordinates of the vertex give us what we're after. The x-coordinate, or I should say t-coordinate, of the vertex is the time when the rocket gets to the maximum. And then the y-coordinate, or I should say h of t, is the height at that time. So that would give you the height of the rocket at the time that it makes its peak, because the peak is the vertex of its trajectory, which is a parabola, which is given by the equation that we did on the last board. Okay, so now, if you're really up on your quadratic equations and all the manipulations we do on that, you have enough information to answer these two questions. If you're feeling bold, pause the video right now and do that math. I'm going to break it down a little bit more for folks who would rather hear it explained, but if you feel like you're up on your quadratics and you've maybe already taken a test on them and you're really strong with completing the square and all those things, accept the challenge. Okay, here we are. Get ready for a big pile of algebra. This is where this problem gets pretty tricky, and a lot of calculating and a lot of keeping track with your parentheses. So, like we mentioned before, what we need to do now is convert this standard form equation into vertex form so we can get the vertex, so we can figure out what's going on at that point. So, first step. This is standard form, but it's not in the right order. So I'm going to change that. I'm going to bring the negative 16t squared right up to the front, and then I'm going to go plus 92t and plus 160. So same equation, just I changed the order because we tend to put the squared term first. Certainly, if you've been in my class, we always teach completing a square with a squared term first. So this is a must-do step for this problem. Now, if you recall you're completing the square, you know we don't do that when there's a number in front of the squared term. The completing the square process doesn't allow for that. So what we need to do is factor the negative 16 out of all the terms so that what's left is complete the squareable. So watch this. I'm going to factor out negative 16, open my parens. That leaves my t squared. It's just the squared term. Now if I factor out negative 16 from 92, I'm going to get 5.75 t. And then if I factor out negative 16 from 160, that's minus 10. And this one is minus. Because we factored a negative number out of all three terms, it changes the sign of all three terms. So the squared term was negative, now it's positive. This term was positive, now it's negative. This was positive, now it's negative. Now I forgot one thing. And I see people do this all the time, and it might lead to problems later. Close the parentheses, because this negative 16 applies to everything that's in there, and that will become important in a few steps. So the whole reason we did this is so that we can complete the square on these three terms, because now it is complete the squareable. So the next step was to figure out what b over 2 squared is. And if you're forgetting what your b term is, your b term is this one here. The a is 1, the b is minus 5.75, and the c is minus 10. We really only need the b term. So go ahead, pause the video and do that math. Okay, fairly straight up calculation. I just plugged in my negative 5.75, divided it by 2, and then squared it, which gives us a positive 8.27. So there's my b over 2 squared. Now, here's the tricky bit. I'm going to add and subtract it to this expression inside the parentheses. So watch. My negative 16 is along for the ride. In fact, for the whole rest of the time, this is just going to hang out at the front of the equation. We're not going to need to do anything more with it. So inside I have my t squared minus 5.75t. Now I add my 8.27. But I can't just add 8.27 to one side of the equation because I'm going to break it. So guess what? I'm going to just subtract it again right there and then bring my minus 10 down and close my parentheses. Okay? So this expression is the same as this one, but I added and subtracted this term, and what that does is it makes this into a perfect square. Now, I'm not going to review perfect square factoring. We have that on other videos and other portions in the class. But suffice it to say that that means that this piece here becomes something else. So I have my minus 16, the parentheses for the whole thing, and then when I factor this down, perfect square-wise, it gets its own parenthesis, and it's going to be minus half of what that is. That's 2.87. And then I bring my squared up. And now, so I took care of this positive one. I still have my minus 8.27 minus 10, close my parentheses. Okay? Now, actually, let's do one more thing. Let's just combine these. Minus 8.27 and minus 10, that's minus 18.27. So let's just save a whole step of writing on the board. Now, we're not quite at vertex form because I have a set of parentheses here and I have a set over here. Vertex form looks like ax minus h squared plus k. There's no parentheses around the outside. So what I need to do is distribute my minus 16 on this term and on that term. And here's what's going to happen. I'm going to get minus 16 t minus 2.87 squared minus 292.3. So the minus 16 got multiplied on the binomial, didn't do anything to it, have to square it first before you could do that, so we don't, and we like that. This is part of vertex form. And then my minus 16 times minus 18.27 became positive 292.3. Whew. So there's our vertex form. We could go h of t equals that. So, critical thinking step. This is giving us something quite significant for our graph and for answering our first two questions. So I want you to pause the video while I erase this board and put up some new stuff and see if you can come up with what did we learn by getting it into vertex form. Okay, here is vertex form. Tell me the vertex. Pause the video and write down the coordinates of the vertex and come back. Okay, the vertex coordinates are just this number, change the sign, so it's minus 2.87 here, so the x-coordinate of the vertex is 2.87, and then this number just comes down to 92.3. Okay, transfer those numbers onto your graph and come back. Okay, so we just spent a bunch of time in quadratic land. We had a whole board full of nasty algebra. It's gone, whew, but you do need to know how to do that, don't forget. So we had that all board of nasty algebra. We created vertex form. We wrote down our vertex. So far, what we've done here in this stage of the problem is just an algebra paper problem. Finally, what I asked last was for you to transfer this information onto the graph. So all I did is I just wrote the coordinates of my vertex there, okay? Problem is now that we have this graph that tells us of a situation. I got a little tower here, and I got these two picky little questions to answer. So I want you to pause the video and think real hard and come back. Both the answers here are evident in the work we've done. So think real hard, write down some answers, and come back. Okay, our answer is this. 2.87 seconds. That is our time coordinate. So 2.87 seconds is the time coordinate for the vertex. So that means at that time, 2.87 seconds, the rocket hits the highest height it's going to get, because that's how long it takes us to get to the vertex on the rocket's path. Now, what is that height? That's given by the function, or the y value. If you plug this in to any of the parts of the function, any forms of the function, it's going to spit out this number, and that's the height at 2.87 seconds. So that's how we solve this. I went ahead and put that on our problem up here. When does it get the max height? 2.87 seconds. What is that height? 2.93 feet. Question number 3. How long is the rocket in the air? And this could be an important question for the folks setting off the fireworks, because perhaps, like after it explodes at the top of its path, there's still some burning bits, and they know how long they're going to burn for. So they need to know that the rocket's going to be in the air long enough for those bits to stop burning, so they don't land on people or start a fire or anything like that. So they need to know the time that the rocket hits the ground so they can make sure that the burning bits are no longer burning. That's just one reason for why you might want to know that. So the tricky part here is that now we're asking the question in terms of the real world situation. We're not talking about quadratic functions. So you're not getting all the keywords that you've gotten when we did some rote mathematical practice on doing the math that's behind this question. So what I find when I help students with this is that the toughest piece is to get your brain around the question and figure out what it means in terms of maybe the diagram and maybe the equation, so that then you can do the math, which actually is fairly straightforward, to answer the question. So, how long is the rocket in the air? There's another way to ask this question. When does the rocket hit the ground? Right? That's the time it's in the air. That time ends when the rocket hits the ground. So we could say, when does the rocket hit the ground? And that's a more understandable way to phrase the same question. That's the time when it hits the ground. When it's launched, time is 0. So the time when it hits the ground out here is the amount of time it's been in the air. So now there's a basic trick we use to find a time like this. It involves seeing this graph in a way that we think of when we're looking at quadratic graphs just on the coordinate plane, when we just graph them, no rocket situation. So pause the video and see if you can figure out what it is that we're being asked to find in terms of quadratic equations. Okay, if you came to the conclusion that we're being asked to find the x-intercept, you're right. The x-intercept is where the height goes to 0 and the function, a pure function, crosses the x-axis and goes into negative land. Fine. Rocket's not going to do that. It's going to hit the ground and stop there. But it is the x-intercept. It's where the path crosses the x-intercept, where the height is 0. So that's what we're being asked to find. So we could rewrite this again. Find x-intercept. So this is interesting. To answer this question, you have to rephrase it to when does it hit the ground, so you understand where the rocket is, and then you have to look at where the rocket is and translate that into quadratic language to say that we're finding an intercept. So actually, quite a bit of steps in there that are all critical thinking steps. We're not doing any algebra, solving equations, doing all that stuff. We're just thinking about the situation, the real world situation, and applying math to it to answer a real world question. So, now that you know you're trying to find the x-intercept of this equation, I want you to pause the video and figure out what the first step of that is, because I think that's also a little tricky. Okay, that first step is to realize that at the ground, the height, which is h of t, is equal to 0. Makes sense, right? Hits the ground, it's got no height anymore. It was launched from 160 feet, it got all the way up to 292.3 feet, and then it came all the way back down to the height was 0. So we know that it hits the ground at the height equal to 0. So now all you got to do is set the equation equal to 0 and solve for t. So what I'd like you to do is just that. We've done all the techniques to solve this equation for t. You've got to get it, it's all kind of wrapped up in a whole bunch of stuff right now. So you have to gradually pick it apart and transfer all the numbers to the other side so that t is alone by itself, and then you'll know what t is. So pause the video, see how far you can get on that. So the first thing I did is I like to work with positive numbers if I can. So I just moved the negative 16t minus 2.87 squared to this side, which made it positive. Remember, I'm trying to get t alone. It's still buried. It's inside this parenthesis with a squared and a 16 on the outside. My first step is going to be to divide through by 16. So I'm going to do that. So when I do that, I end up with just my t minus 2.87 squared, and 292 divided by 16 gives me an 18.2. Now I'm ready to take a square root. To get in here, I got to ultimately get this 2.87 away from my t, but the whole thing is squared. So I'm just going to take the square root of both sides, and that is going to get rid of the squared here, and I have t minus 2.87 equals the square root of 18.2. I need to look. Okay, I got 4.27. There's something missing. Tell me what it is. It's the plus minus. Whenever you take a square root, you have a positive and a negative root. Okay, to finish it up, we're just going to add 2.87 to each side of the equation. T equals 2.87 plus minus 4.27. So I have two solutions, which makes sense. Not every parabola. If a parabola crosses the x-axis once, goes all the way through it, it's going to cross it another time as well. In that case, the pure parabola of this one crosses the x-axis down here when time is negative. But when time is negative, that does not make sense for our real world situation. So one of our solutions we're going to throw away. So let's take a look at this. Okay, so when I do this, when I add 2.87 to 4.27, I get 7.15 seconds. So that makes sense. That is this spot right there. That's 7.15 seconds. So that's how long the rocket is in the air. That's when it hits the ground. That's the x-intercept. So I've come all the way back. I've marked that on my graph. And then my negative solution is 1.39, negative 1.39. So that's this number here, minus 1.39. And again, this number is not relevant to our real world situation, so we just don't pay attention to it. It does not matter for our problem. So that was the third question. So to summarize, if I gave you this problem with all the usual prompts, like factor out a greatest common factor to get rid of the negative 16, you'd do that. If I said, now take these parentheses and complete the square on this part, you could do that. And then if I said, finish up the math, combined like terms, do all that, you could do that. State the vertex, you could do that. You would be just fine with that. If I said, now you have a graph, label your vertex, you'd be able to label your vertex. But this problem is all real world. And so you have to bring your quadratic understanding into this situation and solve and answer it. So yes, I will test you on your ability to do that. I might not make the algebra as painful, but you're on the hook for doing something like this. Now that you've watched the video, take a moment to write down any questions so you can bring them to our next class. Always remember, you can watch the video again to deepen your understanding. If you enjoyed the video, please click like and subscribe.